Hi, my name is Junho Kim from Seoul National University. In this video, I'll present our paper titled LDL, Line Distance Functions for Panoramic Localization. LDL is a localization algorithm that takes a panorama image as input and finds the camera pose with respect to a 3D point cloud map. Unlike many localization methods that pre-collect large amounts of viewpoints and costly visual features, we utilize the 3D point cloud measurements to serve as priors for localization. In addition, to further reduce the map size and attain robustness against 2D-3D domain gaps or illumination changes, LDL exploits line information during localization. This is in contrast to many prior methods that use photometric cues, which are susceptible to the aforementioned issues. LDL performs localization through a three-step process. First, LDL extracts lines, principal directions, and local feature descriptors from the panorama and point cloud. The entire process is fast and efficient, and provides sufficient cues for a robust and accurate localization. Then, LDL performs coarse pose search using novel line descriptors called line distance functions. We compare the holistic distribution of lines decomposed along the principal directions. Compared to establishing individual correspondences between lines, our approach is free from data association errors and can quickly compare large amounts of candidate poses. As the final step, LDL applies local feature matching between the panorama and selected poses within the map to obtain the refined pose. Now we will look at the localization pipeline in more detail. During input preparation, we first extract line segments and principal directions for coarse pose search and local features for refinement. A similar process is repeated for 3D, where we render synthetic views from the point cloud and extract local features for each view. During coarse pose search, we exploit line distance functions in 2D and 3D. First, 2D line distance functions are defined as the spherical distance to the nearest line segment. 3D line distance functions are similarly defined for pool of poses within the map. Specifically, for each pose, we first project the 3D line segments onto the sphere and compute the line distance function values. Here is a visualization of the 3D line distance functions. The 2D and 3D line distance functions are compared, and poses with similar distance function values are selected for refinement. To enhance coarse pose search performance, we decompose line distance functions using principal directions. Specifically in 2D, instead of defining a single distance function using all visible lines, we define 3 line distance functions for each set of lines parallel to the principal directions. We can extend this to 3D by defining 3 decomposed line distance functions for the pool of poses within the map. The decomposed line distance functions are finally compared using a robust cost function. Here, the cost function is defined for each rotation and translation within the map, and compares the decomposed distance function values for uniformly sampled points on the sphere. The localization performance of LDL is fast and accurate compared to the baselines. LDL shows performance on a par with conventional structure-based methods and line transformers that exploit neural networks such as NetFLAD for pose search. Notably, LDL can achieve such results while maintaining 2 orders of magnitude shorter runtime for pose search. In conclusion, we propose LDL, a line-based algorithm for panoramic localization that is robust to 2D-3D domain differences or illumination changes, while maintaining a small map size. LDL uses line distance functions that effectively describes the holistic distribution of lines in 2D and 3D for accurate pose search. Experiments verify that our method can indeed perform effective line-based localization with a fast runtime. Thanks for listening.